Welcome to this lecture on exponential growth. We're going to, in this lecture, look at where exponential growth comes from and look at some examples of algorithms that have exponential growth running times. Exponential growth runtimes appear whenever we're increasing the size of the input by just one multiplies the runtime. Okay, so here's a demonstration of this. If the input of the algorithm is n, then what we do first is we double x n times. So in other words, we compute x times 2 to the n, right? X equals 2 to the n. That's what we do here in this calculation. And then we simply iterate that many times and print out x, and print out the values. And so if we called demo x on with an input of 1, it would print out 1, 0. If we called it with an input of 2, it'd print out 3, 2, 1, 0. If we called it with an input of 3, it would start at 7 and print down to 0, right? So you can see that if I increase the number just of the input just by 1, it doubles the number of outputs that come out. And if I were to put in 10, right, then that would print out 1,000 numbers. Okay, so this is the exponential running times come from when we increase the size of the input by just 1, we are actually multiplying the amount of work that we have to do by a constant factor. So a good example of this is if you wanted to brute force crack your own password because you forgot it. Suppose you forgot your own password, but you know that its length is n, so say 10 characters long or something, and the password is only using binary digits, so only zeros and ones. How long would it take you to guess all the passwords until you guessed it, right? Well, how long does it take? Well, there are n binary digits. Each has 2 options, 0 or 1. So you have 2 options for the first digit, and you have 2 options for the second digit, and you have 2 options for the third digit, and so on, right? And you have n of these digits that you have to choose. So you have 2 times 2 times 2, n times. So that's 2 to the n such different passwords. So brute force password cracking is a good example of an algorithm that takes exponential time. It's exponential in the length of the password. Notice that it would be twice as hard if the password just became 1 digit longer. So assume that you wrote a program to do this and it can guess all 20-digit passwords in 1 second. And notice that 20-digit binary password is still about over 1 million options, right? Because 2 to the 10th, a 10-digit password would be 2 to the 10th would be 1,024. And this is 2 to the 10th times 2 to the 10th, 2 to the 20th, which is about 1,000 times 1,000, which is it's about 1 million, a little more. So suppose your computer could guess or try 1 million passwords in a second. Then if you just added 1 more digit to the password, it would take 2 seconds, obviously, because you have 1 more digit, it's twice as long. But if you upped that by 10 digits to 30, then it would take 2 to the 10th longer, right? Because you're multiplying by an additional 10 digits. 30 minus 20 is an additional 10, so you're multiplying by 2 to the 10th, which is 1,024 seconds, right? Which is on the order of minutes to hours. If you ramped it up to 50 digits, it would take an additional, beyond the 1 second, it would take an additional 30 2 to the 30th attempts, right? Which is about 1 billion seconds, which is about 32 years, okay? So these things grow rather quickly. Just going from 20 digits to 50 digits goes from 1 second to 32 years. Now, another example that you might be surprised at is the maze search that we did for Project 1. Remember that the maze search uses depth-first search, and we go right, down, left, up as far as possible, and then we backtrack if we get stuck. And one of the issues with Project 1 is that the way I've constructed it, the way I told you to do it, is that we don't remember places that we've been that required backtracking. So we might explore the same locations many times, okay? So if you start here, this becomes especially true in a maze that has no solution. So this is a maze with no solution. Let's suppose you can't go to these 3 locations, right? So there's no way to get from the start to the end, assuming that these other ones are valid locations. What would the algorithm start by doing? It would start by going this way and then down and then left and then down, right? And then it would get stuck there, and it would backtrack, and at some point it would backtrack all the way to, let's see, it would backtrack to about here, and then it would go, instead of going right here, it would go down and then right and then up, right? But it's already searched these locations, so why would it do that again? Well, because we don't remember where we've been, because I told you not to do that, okay? Every additional location that we add in this impossible maze has up to 3 neighbors, right? So if I made this maze go way out here, right, and I added more neighbors, right, but I still made this maze impossible to solve, you know, this, if you're coming in from here to this location, it has 3 other neighbors that it could visit, right? So the search actually can take up to 3 to the n time, where n is the number of valid locations. So you can see that very quickly, if we had an unsolvable maze that was quite large, and we can reach a lot of it, but not the end location, this would take a long time. And so even for this tiny maze that I just drew right here, right, this one, just right here, it goes through 120 iterations in order to determine that the maze isn't solvable. So I wanted to show you what this actually looks like without drawing it. And so here's my simulator. We start at the top left up here, where this V is right here, okay? And I'm just gonna run through this quickly, not waste your time too long on it, but it's gonna go through all these iterations, go down, it's gonna get stuck here, and then it starts backtracking. And as it backtracks, it's going to get all the way back to here. And now, instead of going right from this location, from the 0, 1 location, it's gonna go down. And then it's gonna go right, and then up when it can. And then it's gonna get stuck here, and it's gonna backtrack and backtrack. Now it's gonna go left. But look, we've already explored these locations. So I'm gonna just speed this up a little bit. You can see, look at all this. It's doing all this repetitive work, and it does 120 iterations before it can determine that there's no solution. And you'll notice this is a tiny maze. It only has, what, 9 valid locations, including the start and the end, and it does 120 iterations. If I just doubled the size of this, that would blow up the number of iterations to a ridiculously large number. It'd be 120, again, a factor of 120 times longer than that. Okay, so I do want to emphasize that the fact that we don't remember where we have been and we go ahead and re-explore places that we have been in Project One is not an inherent part of the depth-first search, and it's not an inherent part of Project One, okay? So I don't want you to get the wrong idea that depth-first search is somehow inherently slow. It's not. We could have fixed this, and we still could fix this problem of exponential running time by keeping track of every location we visited and never revisiting the same location twice. If we ever visit it, determine that it's a dead end, we would never go back there again. For Project One, we don't do that, and the main reason is to keep it simple, okay? Now, I want to draw your attention to a relationship between the last lecture on logarithms and this lecture on exponentials. Exponential and logarithmic growth are inverses of one another, because with exponential growth, every additional piece of information we add or every additional step multiplies the work by a constant. And with logarithmic growth, every additional step that we take in the algorithm divides the work by a constant. And the math supports this too, right? If we have an exponential base b to the n, and we take the log base b of b to the n, that's equal to n, right? So these are inverses of one another. Log base b of b to the n is equal to n. And so when you think logarithmic runtimes for algorithms, you think, oh, that's a really fast algorithm. And when you think exponential running time for an algorithm, you think, oh, that's a really slow algorithm. Last comment is comparing exponential running times to factorial running times, or exponential and factorial growth. Factorials, you know, n factorial is 1 times 2 times 3 up to times n. These grow even faster than exponentials. So 2 to the n is equal to big O of n factorial. We could even say little o of n factorial. That's partly important, but what I do want to emphasize here is where might we see factorial growth? Factorial growth occurs when we're searching all orderings of n things. Okay, so if what you're doing is you have, say, a combination lock, where we have to order all n numbers. So this is not your standard combination lock with 3 numbers. This is a combination lock with, you have to pick the first number and the second number and the third number all the way up to the last number, and they all have to be different. Then you have n options for the first one and n minus 1 remaining options for the second number and n minus 2 options for the third number, and these multiply together to give you n factorial. You may have heard of the traveling salesperson problem with n cities. And the traveling salesperson problem is you are a traveling salesperson. You need to drive or walk or whatever, or fly to different cities and return back to your home. And you want to do that in the shortest way possible. So you have n places to go. You have to go to all of them. In what order should you go to minimize your total travel cost? Naively, we can solve that in n factorial time. There are faster solutions, but the naive solution is n factorial. And there's also, jokingly, the BOGO sort algorithm. The BOGO sort algorithm is the sorting algorithm which simply tries all reorderings of an array until you find the one that's sorted, right? And that runs in n factorial time because it tries potentially all reorderings of the array. So I hope that gives you some insight into exponential running times and factorial running times and how they're related, and how they relate also to logarithmic running times.